Okay, welcome to the next lecture of ES 300. Today we're going to talk about hydropower. So, three quasi-final exam questions for today are: what are the advantages of hydropower over thermal generation, which would mean nuclear, coal, and natural gas, and other types of renewables? What are the environmental impacts associated with conventional hydropower dams, and in what parts of the world is hydropower growing, and why isn't it expanding in the United States? So hydropower is the power derived from the energy of falling water, so the potential energy of water falling from a vertical distance and running water, which may be harnessed for useful purposes. We've been using hydropower for a really long time, but it wasn't until 1848 that the operations of hydropower were converted to enclosed turbines as opposed to open water wheels. This was done by James Francis. And what he was able to do is attain a 90% efficiency at converting the kinetic energy of the moving water to electrical energy. So just to put that in perspective, 90% efficiency at converting kinetic energy here to electrical energy is far superior in terms of power plant efficiency to a lot of the other conventional technologies that we've discussed so far. Remember, coal and nuclear, the process from taking the embedded chemical or atomic energy in nuclear fuel and coal, converting that to thermal energy through either a combustion or a fission process, converting that thermal energy to kinetic energy in the steam, and then that kinetic energy to electrical energy. Along the way, we lost about 60 or 70% of the actual energy associated with the fuel to heat. And in natural gas combustion turbines, it's even worse. They lose about 75 to 65% of the heat or the energy to heat. And then in natural gas combined cycles, which are the most efficient conventional thermal generation we have, the efficiency was only 60%. Because they were able to use the waste heat from the combustion process in a steam generator in the combined cycle units. Hydropower as a 90% efficient process is pretty remarkable. So this is what an enclosed hydropower turbine looks like. The two big circles on the right are called penstocks. They're the delivery mechanisms for the water that's being delivered from up above, and then it's being shot into this turbine, which the force of that water moving from a greater height is spinning the turbine, which again is just a coil conductor that's located within a magnetic field, so it generates an electrical current. So just to give you some perspective, this is one of the turbines that's installed, or that was installed in Grand Coulee Dam in the Columbia River Basin in Washington. The Grand Coulee Dam is one of the largest hydroelectric dams in the United States. And so here's a picture of Grand Coulee. So again, the basic premise for generating hydroelectric power is that you have some sort of dam, and the dam is used to store water in a reservoir, and so the water level in the reservoir is significantly higher than the actual turbine. So when water is taken in through a penstock and used to spin the turbine, it's taking advantage of that height difference to sort of propel the water through the turbine. So that water is spinning the turbine, generating electricity, and then it's released downstream. So we can calculate the power available at a hydroelectric dam using this equation, where P is equal to the power that's available, N is the dimensionless efficiency of the turbine, which we said is on the order of 90%. Sometimes it's not quite that high in practice, but it's usually pretty high, 80 to 90%. Rho, the sort of P-looking value here, is the density of water in kilograms per cubic meter. Q is the flow rate of the water through the turbine in cubic meters per second. G is the acceleration due to gravity, so meters per second squared. And H is the height difference between the inlet for the turbine and the outlet in meters. So this shows you, for that same schematic, what we're referring to when we say hydraulic head. So this is the force in a way that's propelling water through the turbine. So that force that's available to spin the turbine is a function of the vertical difference between where the water is coming out from the turbine and where the water is coming in. And so what that means is that the more water you have in a reservoir, and the taller the reservoir is or the dam is, the more electricity you can produce for the same unit of water that's moving through the turbine. So based on this understanding of the equation for the available hydropower, where do you think the best places to build hydroelectric dams are? So generally we want high flow because hydropower, the flow rate of water through the turbine is directly proportional to the amount of power we can generate. So we need a high flow rate. We also might look for steep geographical relief and a narrow river inlet. So we want steep geographical relief in order to build tall dams to take advantage of hydraulic head and narrow river outlets in order to build smaller dams across an opening. And narrow river outlets in order to build smaller dams and have lower surface area. So we'd have the same amount of water stored for a smaller surface area. And the advantage there is it would decrease evaporation. So we might look for an area that looks a little bit like this. So this would provide us an ability to store water, a lot of water, and build a tall dam to take advantage of high hydraulic head. We wouldn't have to build a dam too far across the opening here, so this is a fairly narrow inlet, and that would also give us a chance to build a reservoir that has a large volume but low surface area in order to minimize evaporation. So when we hypothetically build this dam, we would build it across this opening, and then water would store up behind it, so it would create this giant reservoir behind the dam. And you can sort of see from this picture the previous contour of the river, in this case the Colorado River, shown in that sort of dotted line, and then you can also see compare that to what the size of the reservoir would look behind the dam. So one of the principal things to understand is when you build a dam, you are flooding a giant area behind the dam that was previously not flooded. And so the way that this would work is that if we wanted to build this dam in this particular opening, we would need to temporarily divert the flows of the river away from the actual construction site of the dam. And so we would blast through the adjacent rock and hill slopes tunnels that could be then used to divert water away, and then the water would eventually reconnect with the river, but downstream of where we want to actually build the dam. And we might include some sort of temporary barrier or dam as well above the construction site or upstream of the construction site to keep water away from it. And then the process of building the dam itself is a significant engineering challenge. We're not going to talk about that as much in this class. And then once the dam is complete, the reservoir has to fill up with water, and that can take years. If the dam is big enough and the reservoir storage capacity is large enough, the flow of a river might take quite a long time to actually fill up the reservoir itself. And if you hadn't already recognized it, the sequence of photos I just showed you were from the construction of the Hoover Dam, which is in Nevada. It dams the Colorado River. It's a significant amount of a source of hydroelectric power for many states, Arizona, Nevada, as well as Southern California in the United States. And this is one of the more iconic looking hydroelectric dams that we have. Here's a view inside the powerhouse of Hoover Dam. So each one of those sort of cylindrical structures is part of the components for a single hydroelectric turbine that would be generating electricity. And so I see at least 6 here, and I think that might be all the turbines they have there. The Hoover Dam is a massive dam in terms of its hydropower capacity, so its installed capacity is in the thousands of megawatts. And so just again to give you a sense of scale here, the penstocks that would be delivering water to the Hoover Dam are gigantic, so about 30 feet in diameter. So imagine this much water coming through these giant penstocks from the Colorado River or the reservoir behind the Hoover Dam, and being funneled down through the penstocks to the turbines, which spin to generate electricity. Okay, so there are 3 different types of hydropower in general. So there's conventional run-of-river, and pump storage. So let's discuss all three. So with conventional hydropower, dam operators are using the reservoir to store water inflows when electricity is less valuable, and they hold that water until a later time when electricity is more valuable. And so this strategy can be enacted on multiple timescales, so seasonal, daily, and hourly. And so just to give you a sense for kind of what that looks like, the top part of this figure shows the reservoir elevation, so it would be the amount of water that's in the lake. And on the x-axis here, you have the day of the year. So this is seasonal. This is actually a reservoir elevation guide curve from a federally owned reservoir on the North Carolina and Virginia border. And so what we can see here is that the reservoir is storing water during the first half of the year. And that tends to be when there are higher inflows. And so the reservoir stores the water and the lake level increases. And this also tends to coincide with a period when demand for electricity is lower. And so later in the year when electricity demand is higher, and also coincidentally when there's less water flowing into the reservoir, the dam is discharging all of its water. So hydroelectric dams can also pursue a similar strategy of holding water when electricity is less valuable, and then releasing water in order to produce electricity when demand is higher. And so they do that in their role as a peaking resource. So when demand for electricity is low, they're just holding water and releasing as little as possible. And then when demand increases, they start to release water and produce electricity. So many conventional hydroelectric dams are also multi-purpose. So they're built by the U.S. federal government to provide flood control and water for irrigation. And in many cases, hydropower is sort of the afterthought. A lot of the dams that were built by the United States were primarily for flood control and water for irrigation, particularly in the arid West. In terms of irrigation, flood control dams were built throughout the United States, and the incorporation of hydropower as an objective in the operation of these dams was something that was seen to be able to sort of pay for the other services that the dams were providing in addition. So here's a picture of Portland, Oregon in 1861. So Portland is right on the Willamette River, which is a tributary of the Columbia, and so there are many parts of the country that dealt with massive, catastrophic flooding throughout the United States until flood control reservoirs were built, many of them built by the U.S. federal government. So the two parts of the federal government that are responsible for building a lot of the dams in the United States are the Army Corps of Engineers. So the Army Corps of Engineers mandate for building dams and constructing reservoirs were for hydropower, but primarily for flood control and navigation, as well as water supply. And so the Army Corps of Engineers geographically was sort of focused all over, a lot of it on the East Coast. And then out west in the arid West, the main purposes of building some of these dams were to provide electricity through hydropower and also water supply for irrigation. And so a different federal agency has been traditionally in charge of building and operating many of the dams out west, and that's the U.S. Department of Interior, specifically the Bureau of Reclamation. So today, about 52% of U.S. hydropower capacity in the United States is owned and operated by federal entities. The other 48% is owned by private and public entities, municipalities, and others. So that's conventional hydroelectric dams, where they're really strategically using the reservoir to store water when it's less valuable, not just for hydropower production, but also for water supply for irrigation, and as a service in providing flood control, and then releasing the water either gradually or, again, strategically to maximize the value of hydropower production or water. Run-of-river hydroelectric dams are more passive. So they are dams, but they don't really store inflows. So electricity generation is driven entirely by river flows on a daily basis. So whatever comes into the reservoir is pushed out pretty much immediately. And so these hydroelectric dams are a little bit less flexible in terms of timing their energy production to maximize its value, but they're still they're very valuable to have. So an example of this would be Chief Joseph Dam. Again, this is also in the Columbia River, the same river as Grand Coulee Dam in the state of Washington, right on the Oregon and Washington border. So often the way that dams are constructed are in what's called cascades, and this is where you have an upstream conventional dam and a downstream conventional dam, and those dams have reservoir storage capacity that's used strategically. So when there's a lot of water flowing downhill, for example, during a wet season on the East Coast, or during summer snowmelt on the West Coast, those dams are used to catch that big pulse of water that's coming downhill and store it for a later time. And then in between the two conventional dams, you have run-of-river dams that have less control over the storage and release of water. So these three run-of-river dams would be entirely dependent on the decisions that are made at the upstream conventional dams in terms of the availability of water. However, if we assume that the conventional dams are making decisions that are beneficial for the timing of hydropower production, then the placement of run-of-river dams in the middle would be able to take advantage of that. And so this is one way of sort of maximizing the amount of power you can get for the same flow of water on the same river, is to have run-of-the-river dams sort of interspaced between conventional dams, so they're able to just generate electricity as it flows downhill. So the third type of hydropower I want to talk about is pumped storage, and this is actually a type of energy storage mechanism that operates a lot like a battery. So the deal here is that you have two reservoirs that are separated spatially, but also vertically from each other. So you have an upper and a lower reservoir. And the way that these are used is that you're pumping water from the lower reservoir to the upper reservoir at night. So you're actually consuming electricity when electricity is cheap, when demand is low. And then you're releasing the water from the upper reservoir to the lower reservoir, so you're generating electricity when electricity is expensive during peak hours. So this is what one might look like. So you'd have a lower reservoir and an upper reservoir. So you're pumping water up through a mountain when electricity demand is low and the price of electricity is low, and then you're releasing water back through the same structure and generating electricity when demand is high. So why do this? Well, they really serve the same function as batteries. So within the context of a competitive wholesale electricity market where you have a price that's going up and down constantly, if you had a pumped storage hydroelectric dam, one of the things it could do is buy electricity when it's low in price and then sell it a little bit later when it's high in price. So this would be called price arbitrage, so buying low and selling high. So it would make a profit on every megawatt hour of electricity that it sells. Now, overall, it might be a net consumer of electricity. So pumped storage dams, similar to batteries, are not producing electricity. In fact, they're actually overall a source of demand on the grid, but they do provide this valuable service in helping to shift the timing of generation. So when generation is cheap and plentiful, they're storing it, and then they're shifting when that generation is available to a later part of the day when electricity is more scarce and more expensive. So let's talk about hydropower's role in the U.S. power mix. So today, hydropower provides about 7% of the generation that's used in the United States. This can vary a little bit year to year based on hydrology, so how much it rains and how much it snows. But in general, the average is on the order of 7%. Now that mix, the importance and the share of hydropower in the generation mix can vary tremendously depending on what state you live in. There are some states throughout the U.S. that are much more reliant on hydropower, for example, in the Pacific Northwest and some parts of the Northeast. And the reliance here on hydropower is due to the proximity of available resources. So there are lots of hydroelectric dams in the Pacific Northwest because there are good places to build hydroelectric dams in the Pacific Northwest. A lot of water, steep geographical relief. So all the things we talked about, all the characteristics that you would need to build to find an ideal place to build a hydroelectric dam Those places are more plentiful in the Pacific Northwest, as well as the West Coast in general. Much less plentiful in the Midwest, obviously, not much changes in elevation, and on the eastern coast. So within the generation mix, hydroelectric dams are similar to renewables in that they have variable costs that are essentially zero because there's no fuel cost. So after you build the hydroelectric dam, the variable cost of producing electricity is essentially zero. In terms of plant flexibility, these are extremely fast. Hydroelectric dams are among the most flexible types of generation that we have. They can stop and start extremely quickly, on the order of minutes, and also ramp up from 0 to 100% of capacity in minutes as well. So what that means is that in most systems in the U.S., hydropower is used exclusively as a peaking resource, both due to its operational flexibility, but also relative scarcity. So if you don't have much hydropower, which is what most of the United States is in the situation of, then you only want to use it when it's most valuable. And so you wait until the price of electricity is really high or demand for electricity is high, and you only use it during those periods. And so that's why in most conventional systems we see hydropower being used as a peaking resource, so it's only being used during those high demand periods of the day, in a very similar way that we see natural gas power plants being used, at least traditionally. So the difference between hydropower and other renewables like wind and solar is that you can schedule hydropower. So even though the costs are both $0 per megawatt hour, unlike wind and solar, hydropower can be scheduled and turned on and off very quickly. So one of the exceptions to this situation in which hydropower is used exclusively as a peaking resource are areas of the country that are reliant on hydropower for significant amounts of generation. And one example would be the Pacific Northwest, where much of this region is served by a utility called Bonneville Power Administration. So Bonneville is technically part of the U.S. government. So this is the part of the U.S. government that markets the electric power that's produced by federally owned hydroelectric dams in the Pacific Northwest, and it also delivers electricity via transmission lines to retail utilities, who then deliver that electricity to retail consumers. And so a lot of the dams that are located in the Pacific Northwest are located in the Columbia River Basin, which is the extent of that is shown here in green, and all the different circles are hydroelectric dams that are located within this basin. And so there's about 22 megawatts or gigawatts of hydropower capacity that exists in this basin alone. So that's about the same amount of generation that Duke Energy owns in North Carolina, or in the legacy Duke system in North Carolina. And so this amount of hydropower capacity does actually meet about 60% of regional electricity demand. So hydropower here is used a bit differently, not just as a peaking resource, but also as a source of baseload generation. So continuing with our discussion of hydropower and renewables, one of the important aspects of hydropower in terms of its operational flexibility is its capability for helping to integrate renewable energy. So remember, variable renewable energy like wind and solar, because they're intermittent but also somewhat unpredictable, they can increase the need for flexible generation resources and operational reserves. So we'll talk about why this is in the next week or two. But hydropower is in some ways an ideal complement. We talked about how natural gas combined cycle plants are a blue bridge to a green future potentially because of their flexibility. They complement the intermittent and uncertain nature of renewables quite well, and hydropower is the same. So dams, because they can turn on and off quickly and ramp up and down quickly, they're able to compensate for variability and variable renewables. So when wind and solar are low, you can increase hydropower production, and when wind and solar are plentiful, you can decrease hydropower production. You can also provide backup power or operational reserves to ensure against any time when you think wind is going to be available, or you think when solar is going to be available and it turns out not to be. Pump storage, apart from just conventional hydropower and its operational flexibility, pump storage could play another role here, and that's because pump storage has this unique ability to consume electricity. And so one of the things that we could do with pump storage, the same way we're anticipating being able to use, for example, lithium-ion batteries, is a way to absorb renewable energy production when it's plentiful and when potentially it's not needed, and then discharge it later, discharge that pump storage unit, and then generate electricity when energy is scarce and when renewable energy is scarce specifically. So the idea here is that when wind and solar is available, water would be going uphill. You'd be consuming wind and solar in order to pump water to the upper reservoir, and then when the sun's not shining and when the wind's not blowing, the water would run downhill and be producing electricity. And so this could help address, the same way we're hoping that batteries will help address, the potential for occasional periods of generation oversupply. So one of the issues, especially with solar, but also with wind, is that when you have renewable energy being produced in one geographical area, because of the covariance of meteorological conditions, then you are likely to also have renewable energy available in nearby areas. So if the sun is shining where I live, the sun is also going to be shining probably 20 miles away from where I live, or even 50 or 100 miles away. And the same is true with wind. And so what this means is that you can get into situations where you either have lots and lots of renewables available at one time or none. And so what this figure shows, and we'll talk about this particular figure more, is California's duck curve. And what it's meant to show is that each one of these colored lines is a different year, and it shows that the progressively increasing the amount of solar power on California's grid is causing the demand for electricity from other sources of generation to decrease during the middle part of the day when solar is available. So you get this big hole, or this valley in the middle part of the day, where you don't really need any generation from other sources because you have so much solar available. But then as soon as the sun goes down, your demand for electricity from other sources goes way up because the sun's not shining anymore, but demand is still high. And so one of the ideas with using pump storage is that you could use the solar power to pump water to the upper reservoir during this middle part of the day when you have a lot of solar available. And then later in the day when the sun goes down and demand is still high, you would release that water to produce electricity to meet demand in the later